Hello all, welcome to this course on time series modeling and forecasting using R. Now again, just to give you a very quick overview of where we are standing in this week, and again just to revise a few ideas about the main topic of co-integration. So all this week we have been discussing about what exactly does one mean by co-integration and when can we say that two series are co-integrated, and right. So the idea is that let us say if you have two series x and y, then even if x and y are integrated with certain order, let us say 1 or something like that. So in short, if you remember, we had introduced this notation, right. So xt and yt would be something like I1. So this I1 stands for both xt and yt are integrated with an order of 1, right. But then co-integrated means that if there exists a certain constant or a certain combination of xt and yt, so let us say in some sense you are able to combine xt and yt through some co-integrating vector which is beta, such that any linear combination of xt and yt happens to be I0. Now again I0 stands for that the linear combination is stationary, right, and obviously I1 stands for that both xt and yt individually are integrated with an order of 1. Okay. And by the way, just again to emphasize on the point that integration means non-stationarity. So the moment any time series is integrated with a certain order, let us say 1, 2, 3, etc. So it sort of means that the underlying time series is non-stationary. And again at the same time, the moment the series converts itself to I0, so I0 stands for stationarity. Okay. So here initially we had taken, even in the last lecture or the one before that, that xt and yt are individually I1, but certain linear combination containing that co-integration vector beta happens to be I0. And in this context we say that xt and yt are co-integrated. Okay. Now again, why exactly do we study co-integration? So all these ideas we have studied so far, let us say in the last lecture or the one before that. Okay. But again, a very quick information as to why this entire idea of co-integration is important is that if xt and yt are co-integrated, then there should exist some long term equilibrium between the two series, so xt and yt, right, and whatever deviations happen in the short term. So let us say again, if you remember, we had drawn multiple graphs where let us say this is the overall mean and the series xt sort of converges or diverges like that, and yt sort of converges or diverges like that. So one can actually see that in the long term they have to actually both revert to some possible mean structure, right. So in the longer run they come to some equilibrium, but of course in the shorter duration there might be some deviations from the actual mean, right. Now in this lecture, as the title suggests, we will go forward by discussing a few tests for co-integration and of course a few applications towards the end. Now firstly, what do you mean by tests for co-integration? So all these tests would basically tell us whether xt and yt are indeed co-integrated or not. Okay. Alright, so before we discuss all these tests that you see in front of you in this slide, we will give a very brief introduction to why is testing required, right. So we will introduce co-integration tests now. So co-integration tests are used to determine whether two or more non-stationary time series have a stable long term relationship. So this is the essence here. So if xt and yt are co-integrated, they should actually have a long term equilibrium or they should have a long term stable relationship. Okay. On the other hand, if time series are co-integrated, it means that although they may drift apart in the shorter term, they tend to move together in the longer term. So this is exactly what we discussed just a short while back in the introduction part of today's lecture, and we've thoroughly discussed both these points in the last lecture also, right. So in the short term the two series might deviate from each other, but in the longer term they possess some stable long term relationship. So in this context, following are a few tests in this regard. So how does one test if two series xt and yt are indeed co-integrated or not, etc. Right. So again, just to give a few names here. So the first one is Engel-Granger two-step test. So of course this was given by two people, Engel and Granger. The second one is Johansen test, right. Then the third one is Phillips-Oliaris co-integration test. Now again, I understand that all these names are hard to pronounce, but one can't help it, right. So the third one is Phillips-Oliaris co-integration test. Then the next one is Durbin-Watson co-integration test. And the last one we discuss in today's lecture is called as the autoregressive distributed lag, or in short ARDL bounce test. Okay. So again, just to give you a quick overview once more, that all these tests, the key idea is to test for the underlying co-integration between xt and yt. Okay. So again, if xt and yt are sort of integrated with some order, so now let me in general put id. So the order of integration is id, or rather the order of integration is d. But if there exists a certain co-integration vector beta such that the linear combination of xt and yt becomes I0. Okay. So once you go through this entire process of converting into a linear combination, then if both the series gets converted to I0, not individually. So this is one important part, that individually they would be ID, or rather I1, let us say, right. But any linear combination containing this beta vector, which is called as a co-integration vector, happens to be I0. So then xt and yt would be co-integrated. Now again, all these tests are meant to sort of test this underlying characteristic, that whether xt and yt are indeed co-integrated or not. All right. Okay, so we will start with the first one, which is one of the famous ones, which is called as Engel-Granger two-step test. Now what exactly does one mean by Engel-Granger two-test step and so on? Okay. So the Engel-Granger test is one of the first methods developed to test for co-integration, specifically between any two variables. Okay. And it involves two main steps. So the first step is estimating the long run relationship. Now as we have discussed so far, that if xt and yt are co-integrated, then there should exist some long term equilibrium or long run relationship, and on the other hand there should be some short term deviations as well. Okay. So the first step under this Engel-Granger two-step test is to estimate the long run relationship. And how exactly? So through a simple regression. So the equation that you see here in front of you is nothing but of a simple regression equation, where alpha is the intercept, beta is the slope, xt is the first series, yt is the second series, and epsilon t is the random error. Okay. Alright, so how do you progress with such a test is that regress one variable on the other or others depending on how many series you have to obtain the residuals, of course, right. And what exactly do you mean by residuals? So residuals are nothing but the estimated deviations from the long run equilibrium. Okay. So here, as discussed already, that xt is one of the series and yt is the other series, and we will be regressing yt on xt, right. So beta is the slope, alpha is the intercept, and epsilon t is a random error. So once we run this regression, we will look at the residuals obtained from this regression. Okay. So this is the first step, right. And now the second step is test for stationarity of these residuals. So once you obtain the residuals from the earlier regression equation, then we actually have to test for stationarity of those residuals, and one can apply the famous augmented Dickey-Fuller test, so which is also called as ADF test in short, to test if the residuals are indeed stationary or not. Okay. So I can actually apply this ADF test on the residuals epsilon t, and if it turns out that the residuals are stationary, the other term for stationarity, as we have seen throughout this week, is I0. So I0 stands for stationary series, right. So if the residuals are indeed stationary or integrated with an order of 0, then one can actually safely say that the variables are co-integrated. Okay. So again, just to summarize very quickly, so the first step is to generate that regression equation we saw earlier, where you simply form a regression between one of the series, let us say xt, and the other series yt, using a simple linear regression kind of a structure. So yt equals alpha plus beta xt plus random error, obviously. Then run the regression, obtain the residuals of the regression, and test if the residuals are indeed stationary or not stationary. Okay. So here what could be the null hypothesis and the alternative hypothesis? So for this Engel-Granger test, the null hypothesis or H naught is that the residuals are not stationary, and if the residuals are not stationary, the series is not co-integrated, of course, right. Because if xt and yt or the residuals are not stationary of that regression, then one can actually say that xt and yt are individually, let us say I1 or ID in general. Okay. So the null hypothesis is that the residuals are not stationary, which implies that the series is not co-integrated, or the two series are not co-integrated. And similarly, the alternative hypothesis or H1 is that the residuals are stationary, so that the series are co-integrated indeed. Okay. So I guess this is slightly confusing, but one has to keep in mind that the null hypothesis points to a situation where the series is not co-integrated, while the alternative points to a situation where the series is indeed co-integrated. Now, how about a limitation of this test though? So are there any limitations of this Engel-Granger test? And the answer is yes. So this test is only suitable for two variables and may lack power if more than two variables are involved. Okay. So, for example, even the example we discussed in the last slide, we took the example of two variables, so xt and yt. So, the moment you go beyond two series, let us say xt and yt, one might encounter some problems or some limitations. Okay. So, specifically this Engel-Granger test is kind of superior in a situation where one only has two variables, so or rather two series, let us say xt and yt, and this may lack in power if more than two variables are involved. Okay. Okay, so now the second test in the array of tests is called as Johansson test, and this was of course given by this person named Johansson. So, the Johansson test is a more comprehensive test for co-integration which can handle multiple variables. Okay. So, one drawback that we saw for the Engel-Granger test in the last slide was that it can't perform really good if we extend to more than two variables or more than two series. And this is exactly where the Johansson test comes to rescue. So, again just to summarize, the Johansson test is a much more comprehensive test for co-integration which can handle multiple variables. So, let us say if you have more than two series for some reason, so xt, yt, zt, etc. So, even in such situations this Johansson test proves to be superior. Now, what exactly is the underlying mechanism of this test? So, this Johansson test is based on a vector autoregression, or in short VAR model structure, and examines the rank of the co-integration matrix to determine the number of co-integrating relationships. Okay. So, in short, in the last week if you remember, we discussed thoroughly about VAR models, right, or rather vector autoregressive models. So, this is one of the underlying ingredient of this Johansson test. So, it sort of makes use of a VAR model and examines the rank of the co-integration matrix. So, assume that you have multiple variables, right, for example xt, yt, zt, wt, ut, vt, etc. So, if you have more than two series, I can actually get co-integration matrix, right. So, what I can do is I can pairwise look at co-integrating factors. So, whether xt and yt are co-integrated, or whether xt and zt are co-integrated, or whether yt and zt are co-integrated, right. So, in short, I can get a co-integration matrix which is pairwise. Okay. And such a co-integration matrix helps to determine the number of co-integrating relationships. So, out of all these different series, I can actually get hold of all such pairs which might be co-integrated in a way. Alright. So, the Johansson test is sort of powerful in that sense that by analyzing the co-integration matrix in a multivariate kind of a structure, or rather a VAR kind of a structure, I can sort of determine the number of co-integrating relationships among all these different series. Okay. So, hopefully the idea behind both these tests is clear now. Okay. Alright, so now coming back to the actual Johansson test. So, how do you actually take the approach of testing using the Johansson test? So, again it has two steps. So, the first is trace test, right. So, under this Johansson test you have two more steps to follow. So, the first one is trace test. So, what do you mean by trace test? So, this trace test tests the hypothesis that the number of co-integrating vectors is less than or equal to some constant r against the alternative of more than r. Okay. So, just in the previous slide we have seen that the Johansson test identifies the co-integration matrix, or rather the co-integrating matrix, and tries to identify that how many pairs or how many such series are indeed co-integrated. So, in this period the first step is to actually test the hypothesis that the number of co-integrating vectors is less than or equal to some constant r against the alternative of more than r. And in the same spirit I can actually test using a second approach, which is the maximum eigenvalue test. So, what exactly one means by this? So, such a test tests the hypothesis that the number of co-integrating vectors is r against the alternative of r plus 1. Okay. So, in a way both the trace test and maximum eigenvalue test is sort of put forward a constant r, and then the hypothesis is that whether the number of co-integrating vectors is less than that threshold, which is r, or more than r. Okay. Now, again pointing to what exactly is the null hypothesis for this Johansson test. So, again H naught is there are r co-integrating relationships, right, and on the other hand alternative hypothesis, or H1, is that there are more than r co-integrating relationships. So, of course if one relies on H1, so right, so once you test using the Johansson test and the conclusion is to reject the null. So, if you are rejecting the null, you have to go with the alternative, and if you are going with the alternative, it sort of means that you have more than r co-integrating relationships among all the series, which also means that there is some underlying strong co-integration which exists. Okay. Alright, so now similarly the third one. So the third one is Phillips-Oliaris co-integration test or Phillips-Oliaris co-integration test, right. Now what exactly is this test like? So the Phillips-Oliaris test is kind of similar to the Engel-Granger test. It's a residual based test for co-integration, but uses different test statistics which can be more robust in certain cases. Now again, just for a second, if you go back to Engel-Granger test, right. So what exactly happened there is that we created that regression, if you remember. So yt equals alpha plus beta xt plus some random error epsilon t. And through this regression and the behavior of, let's say, the slope coefficient and the intercept coefficients, we kind of argued whether xt and yt are co-integrated or not. Okay. So in the same spirit, this Phillips-Oliaris test is slightly different from this Engel-Granger structure, in a sense that this is again a residual based test for co-integration, but uses different test statistics other than the used by Engel-Granger test, which can be more robust in certain cases. Okay. So again, just a couple of points to mention here, that if you are already done a course on regression, then whatever I will speak now would be kind of more in relationship to all of you, that if you are setting up a regression model like this, let's say between xt and yt, so any regression has some assumptions, right. So what all assumptions are there in regression? So it has to be a linear model, then errors have to be independent, right. Then one of the other underlying assumptions is that the errors have to follow a normal distribution, and lastly the error should have an equal variance, right. So if any of these assumptions is violated, then we say that a simple linear regression or multiple linear regression does not make sense. So in the same spirit, again, if you come back to Phillips-Oliaris test, what it does, it sort of creates a similar regression model, but using a different test statistic which is slightly different from the model which is written down here, and it so turns out that it can be sort of robust in certain cases. So even though if some of the assumptions of the underlying regression structure is not being met, in such a situation the Phillips-Oliaris test does not fail, right. So this is the underlying idea of why should you use the Phillips-Oliaris test as compared to Engel-Granger test. Of course not in all the situations, but at least in some situations where you require that robustness to happen, basically. Make sense? Now again, as before, what is the null hypothesis or H naught? So H naught stands for no co-integration exists between the series, and similarly alternative hypothesis or H1 is co-integration exists between the series, right. So in all the tests we have seen so far, the null hypothesis is kind of constant, which points to the fact that there isn't any co-integration between the series, and similarly the alternative points to the fact that there is some co-integration existing between the series. Okay. Now by the way, the name of this test statistic is nothing but Phillips-Oliaris test statistics. So this underlying test uses the Phillips-Oliaris test statistics to evaluate the stationarity of the residuals from a long run regression. So let's say you create this regression with slight modification, you obtain the residuals, but then the test statistic under the Phillips-Oliaris is slightly different than the Engel-Granger. Make sense? Alright, so the next one is called as Durbin-Watson co-integration test. So what exactly goes in this is that the Durbin-Watson test is not a direct co-integration test as written down here, but in other words it can help in testing for spurious relationships. Now again, I am pretty sure that in the very first lecture of this week we talked about spurious regressions, right. Now again, just to give you a quick overview of what do you mean by spurious regressions or spurious correlations or relationships, is that even though two variables, let's say xt and yt, are not at all related, but once you create a normal regression model between xt and yt, or you try to find out the correlation between xt and yt, it turns out that the correlation value is high or the regression is also seeing a very good fit. Okay. So such relationships are called as spurious, because even though xt and yt have no relationship between themselves, but still the correlation or the underlying regression is pretty strong. Okay. So in such cases where a regression's Durbin-Watson statistic is close to 0, it suggests the possibility of a spurious regression. Okay. So in situations where you have spurious regressions, I can actually find out the value of the Durbin-Watson statistic, and if the value of the Durbin-Watson statistic is close to 0, it suggests the possibility of a spurious regression, indicating that the variables may not be co-integrated. Okay. So again you have to go back to all the examples you have discussed in the prior lectures this week, that the moment a spurious regression exists between xt and yt, it sort of indicates that the variables may not be co-integrated. Okay. Secondly, if the Durbin-Watson statistic is above some threshold, so let us say generally above 1.5 or 2, it suggests that the co-integration relationship might exist between xt and yt. Okay. So, couple of things here, that the underlying idea is about spurious regression. So, if spurious regression exists between xt and yt, one can actually go forward by using such a test, which is Durbin-Watson test, right, and one should find out the value of this Durbin-Watson test statistic, and if the value of the test statistic is close to 0, it suggests the possibility of a spurious regression, indicating that the variables may not be co-integrated. On the other hand, if the Durbin-Watson statistic is above some threshold, let us say 1.5 or 2 generally, then this fact suggests that a co-integration relationship might exist. Okay. So, let me write down TS. So, TS stands for test statistic value. So, if test statistic value is close to 0, then co-integration does not exist, while if the test statistic value is bigger than 0, of course, and generally in the threshold of 1.5 to 2, then one might expect that there has to be some co-integration which is existing. Okay. Alright, now the last one is called as autoregressive distributed lag, or in short ARDL bounce test. Okay. So, again just to quickly remind you of how many tests we have seen so far, right. So, again let me quickly sift through all the previous slides. So, the very recent one was Durbin-Watson, just before that we discussed Phillips-Oliaris, just before that we discussed Johansson, and the very first one was Engel-Granger. Okay. So, we have seen 4 tests so far. So, Engel-Granger, then Johansson, then Phillips-Oliaris, and then lastly Durbin-Watson. And now the very last one we will discuss is ARDL bounce test, or autoregressive distributed lag bounce test. Now, what exactly goes inside this ARDL bounce test is that the ARDL bounce test is suitable when the underlying series are of mixed integration orders. So, firstly one should understand that what do you mean by mixed integration orders. So, some are I0, some are I1. So, I will give you an example. So, let us say if you are taking multiple series again, so let us say xt, yt, zt, and let us say wt. Okay. And then let us say if you see combinations between all these series, so xt, yt, zt, wt, and it so turns out that let us say xt and yt are individually I1, and probably let us say zt might be I0, wt again might be I1, right. So, you sort of have a mixed integration order. So, some of the series are I0 and some of the other series are I1 in this entire set. Okay. So, let me write down that some are I0, some are I1. So, there might be one problem when you handle such a set, right. I mean, let us say if xt and yt are I1, so there should exist some linear combination of xt and yt such that it is I0, which means that xt and yt are co-integrated, right. But in the beginning itself, if let us say zt is I0, okay. So, let us say zt is assumed to be I0, while yt is assumed to be I1 as an example, right. So, zt is I0, yt is I1. So, if at all there exists any linear combination between yt and zt which is I0, can we still say that they are co-integrated, because zt itself is I0, isn't it. So, all such intricacies come into picture when some of them are I1, some of them are I0, some might be I2, etc. Okay. So, in all such situations, this autoregressive distributed lag bounce test is kind of suitable. So, again just to summarize, this ARDL bounce test is suitable when the underlying series are of mixed integration order. So, some are I0, some are I1, right. The ARDL bounce test provides critical values to determine if a long run relationship exists between the variables or not. Okay. So, as seen before for all the other tests also. So, again what one gets out of this ARDL bounce test is that it sort of produces some critical values to again determine if a long run relationship exists between the variables or not. So, again what exactly is the null hypothesis? So, H naught is no co-integration. So, there does not exist any long run relationship between the series, and the alternative is that the co-integration exists as before. Okay. So, the ARDL approach is widely used in fields like economics, finance, especially when stationarity requirements are mixed and is flexible with various sample sizes. So, these are some advantages of using the ARDL bounce test, that such an approach can be widely used in areas like economics, finance, especially when stationarity requirements are mixed and is flexible with various sample sizes. Okay, so right towards the end we will discuss a couple of practical examples quickly and then close today's session. Okay. So, the first combination is house prices and rent prices. So, the Engel-Granger test helps to determine if house prices and rental prices share a long term relationship. So, co-integration between these two suggests that despite any short term imbalances, house prices should align with rental values over time, providing insights for pricing in real estate markets. Right? Then the second example could be something like commercial real estate prices and economic indicators. So, what exactly goes inside this one is that co-integration between commercial real estate prices and broader economic indicators such as, let us say, GDP or employment, etc., suggests that real estate prices move with the economy, and such a relationship helps investors and policymakers assess the sensitivity of real estate prices to economic cycles. Okay. Then the third one could be, let us say, healthcare spending and GDP. So, in healthcare, the test helps to determine if healthcare spending is aligned with economic growth. If healthcare expenditures and GDP are co-integrated, this would imply that spending grows with the economy in the long term, which can inform sustainable budgeting and health policy decisions. And last one could be drug prices and R&D costs. So, pharmaceutical companies may analyze if drug prices and research and development costs, or in short R&D costs, are co-integrated or not. If they are co-integrated, or rather if confirmed, it suggests that R&D costs will reflect in long term drug prices, validating the cost recovery model for pharmaceutical pricing strategies. Okay. So, in short, just to summarize, all these examples point to a fact that one should actually test for co-integration in the first place. So, if couple of series are co-integrated, one can actually go forward and analyze multiple other things and then provide some indicators as to why that might happen, or some solutions to handle such co-integrations in practice. Okay. Now, in the next lecture, we will kind of discuss a few more ideas about co-integration, and again the lecture after that would be completely practical. Okay. Thank you.